Hello everyone. Apologies that there's no lecture for this week. Hopefully this presentation will suffice in the meantime. Just a reminder that your problem set number 4 is due on Sunday at midnight. And you'll be writing quiz number 4 in tutorial next week. So let's go ahead and get started. Results. However, I'll hold off on that until next week when we're all together again. One thing that I will tell you is that for the midterm grade, if any of you perform better on the final exam, then I will replace your midterm grade with your final exam grade. So if the midterm didn't go well for you, there's no need to panic at this point in the course. You'll have an opportunity to make up for that with the final exam, and my hope is that the experience that you've gained from writing the midterm will lead to better results on the final exam, and we can talk more about this next week. So let's go ahead and get started with this week's content. So this week we were looking at kinetic theory of gases, Fick's law of diffusion, sedimentation, and centrifugation. These are the areas of the formula sheet that we'd be working from. And let's go ahead and get started with the kinetic theory of gases and diffusion. So in the kinetic theory of gases and diffusion, there's a few questions that we seek to answer. What is a gas made of? How do gaseous particles move? What does the word temperature actually mean in a physics sense? And what does random motion look like when we try to model it mathematically? You this little animation. And what I'll do is I'll link you to the website when I post this, so you can go on and explore this yourself. But essentially what it is there's a red dot here. That's an arrow. There's a red dot there, and these are particles that all have random positions and velocities in a two-dimensional box. And this simulation just shows how a single particle moves around over time. And what it is, it's called a random walk, because we can never really tell what direction the particle will go in the next instant of time, because there's far too many particles for us to reasonably predict the collisions that will take place to cause it to change direction and velocity. What we're looking at here is what would happen if you ran the simulation from the previous page for a certain amount of time and traced out exactly where that red particle moved to. And so there's just 3 different runs of the simulation, and each of them are just isolated from each other, so just 3 separate trials of the simulation, running it for a given period of time, and it just shows that the particle truly does exhibit random motion. It's randomly walking around the two-dimensional box that it's contained within. So how do we describe particles in a box? Well, we can't ever define the position and velocity of a single particle because there's just far too many of them. So instead what we do is we try to mathematically describe the motion of all of the particles together. And we do this by looking at the number of particles compared to the number of particles that have a speed of 0. So the number of particles that have some given speed, Vx, compared to the number of particles that have 0 speed. And what ends up resulting from this is a Gaussian distribution. So there I've drawn the Gaussian distribution there. And what's important to recognize on the Gaussian distribution is that the majority of the particles will have a velocity that's somewhere between negative Vx and positive Vx. So these values are sort of a measure of the overall speed of the particles in general. So most of the particles will be pretty close to a speed of 0. You'll find a smaller number of particles at a greater distance away from 0. And this axis is all scaled based on what the velocity of the particles is based on the kinetic energy that's in the system. Distributions of velocities for particles at different temperatures. On the left, what you're looking at is a distribution of speeds for helium particles at 400 Kelvin. And on the right is a distribution of helium particles at 100 Kelvin. And what we notice is both of them have a slightly skewed Gaussian distribution because it can't be perfectly normally distributed because the particles sort of pile up close to having a speed of 0. But what we do notice is that if we sort of compare what the envelope looks like at like 400 K, all of the particles are sort of pushed towards a slower speed at a temperature of 100 K. So the average speeds of the particles is lower as the temperature decreases. We can do the math for one-dimensional problems, two-dimensional problems, and three-dimensional problems. All of them have different biological applications. And the only difference that happens in the math is that when we're comparing the kinetic energies to the thermal energies, so on the left is the kinetic energy and on the right is the thermal energy, the coefficient in front of the thermal energy changes from 1/2 to 2/2 to 3/2. So what relationship do we expect between the average speed of any given helium molecule at the two temperatures? Well, if we look at the average speed, which is denoted by that's what the triangular brackets represent, is an average. Okay, we can see that in this equation, this is v squared. So if I were to solve that for the average speed, I would have to take the square root of that quantity. So that would be 2 kt over m. And so what we see is that the average speed, which we call the RMS velocity, is proportional So I guess I have to square root this as well, sorry. Yeah, square root of all this is proportional to the square root of the temperature. So as the temperature increases, the average speed also increases, but not linearly. It goes with the square root. The square root of temperature. So we would expect the average speed to double at 400K compared to 100K. Increase the temperature by a factor of 4 means that we increase the speed by a factor of 2. And when you work it out with the specific values for Boltzmann's constant and the temperature and the mass of a helium molecule, that's exactly what you get. So just a note here, often we don't worry too much about the difference between speed and velocity. However, when we're talking about thermal physics, it's quite critical to distinguish between speed and velocity. The average velocity of particles is going to be 0 for any given gas, because for every particle that's moving to the right, you have another particle that's moving to the left with the same speed, and so those velocities will cancel each other out. However, since speed is a scalar quantity, it does not cancel out. And so from this, we recognize that the average speed of the particles actually ends up being an excellent definition of temperature for a gas. And so there's the equation for you right there. The temperature of a gas is equal to the mass of the particles times the average speed squared divided by 3 times Boltzmann's constant. So just quickly here, taking a look at diffusion. So now we're graphing positions along the x-axis rather than velocities, but in many ways the concepts are similar. If I were to take a high concentration of particles and place them in a one-dimensional situation at time 1, over time they would spread out and become further spread out as time goes on and on and on. This is the process of diffusion, just particles diffusing from a high concentration to a low concentration. And so if we were to draw the sort of Gaussian distribution, if this might be for T2, then for T1, you might have a Gaussian distribution that is much tighter, much taller in the middle, but not as spread out. Sorry, my drawing skills are apparently not great this evening. And then if you wait for a longer period of time, the number of particles at each position would decrease, but you would get more and more particles that are further away from the center. So that's the statistical representation of diffusion. Diffusion is this random process of particles bouncing off of each other, which is why the particles move from a high concentration to a lower concentration, because there's more collisions where there's more particles, so they're more likely to bounce away from that area of high concentration. But what we recognize is that the distance that the molecules travel from where they start on average is based on the diffusion coefficient of the particles and time. So they get further away from the origin where they start as time increases. But we need to look at the RMS displacement, which means that we're taking this quantity and we're finding the square root of it. So when we do the square root, we get the RMS displacement. That's what RMS stands for, is root mean squared displacement. So literally the root of the mean of the squared of the displacement, and that's going to be proportional to the square root of time. So particles diffuse as the square root of time. Here's a table showing some diffusion coefficients for different particles. And so then here is a concept question that I would deliver in class and give you some time to think about it. Throughout this presentation, I encourage you to sort of pause the video and see if you can work it out for yourself first. And then I'll take it up with you. So for the solution, or let's read the question first. A grain of sugar is placed in a petri dish, and it takes 8 seconds before sugar is detected at some distance r away. At what time might we expect the sugar to be detected at a distance of 2r? So these distances that we're talking about, r and 2r, those are RMS displacements. And there's a handy equation down here that says that the RMS displacement is proportional to the square root of time. So what that means is if I'm doubling, so if r prime, the distance afterwards, is 2 times the distance before, then the time afterwards, so RMS displacement goes as the square root of time. We can also write this as RMS displacement squared goes as time. Sorry, I should have positioned that differently, but so time goes as, let's write that one more time. Time goes as the RMS displacement squared. So if the RMS displacement is doubling, then the time will be quadrupling. So 8 seconds times 4 is 32 seconds. So it would take 32 seconds to detect sugar at a distance of 2r. Diffusion coefficient will be based on the temperature, the viscosity, and the size of the particle. I put a note there about drag forces, and note that they have viscosity and radius in there as well. So the concepts of drag are related to the concepts of diffusion, which I think makes sense. So then, applying that sort of an equation, we can answer a question like this. So again, pause the video and try to answer this yourself. I'll go through the solution now. Consider 2 different spherical protein molecules where one protein has a mass that's 8 times greater than the other. So we would say the mass of the big one over the mass of the small one is 8. The equation though doesn't have mass in it, it has the radius, so we would need to recognize that the mass is proportional to the radius cubed. Therefore the radius is proportional to mass to the 1/3. So the radius of the big one over the radius of the small one would be 8 to the 1/3, or 2. So what is their relative diffusion constants? from the equation, the diffusion constant is inversely proportional to the radius. So the diffusion coefficient of the small one over the diffusion coefficient of the big one will be equal to the radius of the big one divided by the radius of the small one. And we already know that that is 2. So what's the relative diffusion constants in water? 2. Try to answer it yourself. I'll answer it here. What factors or parameters change in the diffusion constant when we increase the temperature of the fluid? So we look at the diffusion constant equation. Kb, well, that's Boltzmann's constant. Therefore, it's constant and doesn't change. So any answers that have Boltzmann's constant in there cannot be correct. So then our only question is it just temperature, or is it temperature and viscosity? And so we recognize that the viscosity of a fluid does depend slightly on the temperature. Therefore, our answer must be C. So then we ask this question again. Try to answer this yourself. I'll answer it here. Many students get this wrong on the first try, so I'll sort of show you the wrong way and then I'll fix it for you. What is a greater factor in increasing the diffusion coefficient in 80 degrees centigrade hot water over 10 degrees centigrade cold water? So we can see that the diffusion constant is proportional to the temperature divided by the viscosity. So both of those things are going to change. The question is which one changes more. Changing the temperature from 10 to 80 is increasing the temperature by a factor of 8, while the viscosity is decreasing by about a factor of 4, it looks like. So it seems like the temperature increase would be the greater factor. However, this is the big mistake, is that this is not a temperature difference, this is an absolute temperature. Therefore, we must use Kelvin units. And so a temperature of 10 degrees Celsius is like actually 283 Kelvin, and 80 degrees Celsius is actually like 373 or 53, sorry, 53 Kelvin. So the difference here is only multiplying by, like, I don't know, it's like 1.25 or something like that. What is it? I don't know. I don't have a calculator in front of me, but it's like multiplying by 1.3 or something like that. And so the decrease in viscosity is actually a bigger factor there. Random walks in biology. You can read it for yourself, but the point that I want to get through to you is that Boltzmann's constant times temperature is basically can be thought of as a measure of how much energy particles have. And when particles are interacting with each other, this amount of energy is usually how much energy they're going to be trading with each other. It's very unlikely that you're going to find a particle that has like 10 kT of energy. You're going to be much more likely to find particles that have around 1 kT of energy. Okay. We've already talked a little bit about temperature, but a formal definition of temperature. So the concept of temperature is related to the average motion or kinetic energy of the particles. So the number of particles traveling at some velocity v compared to the number of particles that have a velocity of 0 ends up being equal to e to the negative this exponent, which is the kinetic energy divided by the thermal energy. And so the thermal energy is where our temperature is coming from. And so in 3 dimensions, the average kinetic energy of the particles, which is equivalent to the thermal energy, ends up being 3/2 kT. So that's our definition of temperature. The average kinetic energy of the particles is going to be 3/2 kT. So we rearrange that and we get an equation for the temperature of the system, of the particles in a system. And as I said, kT is about the amount of energy that can be gained or lost with collisions. Okay. So this is sort of summarizing that concept again, just tying the equation into the Gaussian distribution of velocities of the particles. It's very unlike, so like here's 1 kT of energy right here in this region. Those are on the order of 1 kT, so you can imagine 10 kT would be way off the scale. Very unlikely to find a particle with 10 kT of energy. This is just showing how the probability of finding a particle at various velocities changes depending on whether you're dealing with 1, 2, or 3 dimensions. This is not a super important concept for us. It's just interesting to note that the probability, the most probable speed in 1 dimension is 0, whereas in 2 and 3 dimensions, the probability of finding a particle with a speed of 0 is 0. And that's just because of the additional degrees of freedom, the different directions of motion the particles can have. This is just tying back that concept of thermal energy and temperature to kinetic energy. The kinetic energy of the particles is the average related to the average speed of the particles, and that is dictated by the temperature of the system. One thing that's interesting to note in all of this is that if you take a gas like air, for example, which is made up of oxygen and nitrogen and water and helium and hydrogen, the thermal energy of the particles is all the same. But because the particles have different masses, and yet they still have the same kinetic energy, the smaller particles will have a higher average speed. And so that's exactly what we see right here. The largest particle in air is oxygen gas. It has the largest mass, and therefore it has the lowest molecular speed. Whereas at the other end of the spectrum is hydrogen gas. It has the highest molecular speed to make up for the fact that it's got lower mass. And in the end, the kinetic energies of those two gases will be equivalent because they're both at the same temperature. This graph here is just showing how the average speed of the particles changes depending on the temperature again. So basically we just see that for warm particles, if we cool down the system, the RMS velocity of the particles will move leftward to a lower molecular speed. Proteins and large proteins are suspended in water at the same temperature. What is the relationship between the average RMS squared speeds of these proteins? So they're at the same temperature, which means they have the same average kinetic energy, and we know that kinetic energy is equal to 1/2 mv squared. So kinetic energy is proportional to, sorry, let me rephrase. So because they all have the same kinetic energy, the kinetic energy of the large ones and the small ones is going to be a constant. So as the mass of the particles increases, the velocity of the particles must decrease. So therefore the RMS velocity of the large ones is going to be less than the RMS velocity of the small ones. And we saw that on the graph on the last page. So I think that that's this answer here. Okay, another question, give this one a try. A mixture of large catalase proteins and much smaller ovalbumin proteins are mixed in a solution at room temperature. Which of the following statements is most true? So this one we have to sort of read carefully. Again, following the same concepts, we know the large ones are going to be moving slower and the smaller ones are going to be moving faster because the average kinetic energies are going to be constant. But let's read the answers. The catalase proteins, which are the large ones, have higher average kinetic energies. The smaller ovalbumin proteins have higher average kinetic energies. Both proteins have the same root mean squared speeds, or both proteins have the same average kinetic energies. So many students would tend to answer B. The smaller ones are moving faster. However, it's important to recognize that kinetic energy is a combination of both mass and velocity, and it's the kinetic energy that's remaining constant. The velocities are changing based on the masses. So the only correct answer then is that both proteins have the same average kinetic energies. So that's an important distinction between the words average kinetic energy and velocity. So looking at diffusion as net motion of particles from a region of high concentration to a region of lower concentration. I think I drew something like this earlier on, much worse version, but the concentration after just 1 second, there will still be a high concentration near the middle. After 4 seconds, they start to spread out, and after 16 seconds, there's quite a bit more spread in the distribution of particles. But in all of this, the RMS displacement goes with the square root of time. This is just a summary of that again. The RMS displacement goes with the square root of time. So then a scientist puts 100, so again, try to answer this one yourself. A scientist puts 100 small particles suspended in water in a petri dish, waits 20 seconds, and then records their displacement on the x-axis. She obtains the following data. What is the mean displacement of the particles? So in order to find mean displacement, what you need to do is you need to take the frequency multiplied by the displacement, calculate what the frequency times the displacement is for each of these, and then find the average. This data is interestingly quite symmetric, so there's sort of the same number each distance away, both on the positive and negative axis. So when we're calculating the mean displacement of the particles, we actually get an answer of 0. Squared displacement. So now we are sort of taking the directionality out of it, and we can do the calculation to show how that happens. So root mean squared displacement means that we need to take the displacement, we need to square it, we need to find the average of that, and then we need to do the square root of that result. So what I need to do is I need to take the frequency at a particular distance away and multiply it by that distance squared to start. So this is going to be 1 times negative 30 squared is 900. This is going to be 6 times 400. It's going to be 23 times 100. This is going to be 0 because the displacement is 0. It's 23 times 100, 6 times 400, and 1 times 900. Okay, all of these are, like, they're all in hundreds, so I guess I can just start adding things up. I might do it over here because I don't really have a lot of space. So you would do something like this. You would get like 900, 6 times 400 is going to be 2400, 23 times 100 is 2300, 0, and then it's all the same numbers again. So 2300, 2400, 900, and then we're going to add all those up and then find the average. So 900 plus 2400 is 3300, plus 2300 is 5600, plus another 2300 is 7900, 8800. Sort of lost track of where I am here. This is what happens when you're not feeling well. Sorry, guys. So 23 plus 24 is 47, plus 9 is 56, and then these are identical, so I get 112, or yeah, like that. That's what I get. Who knows if that's right? I'm pretty sure that's good. Okay, anyways, and then we've got 100 particles, so we need to take the sum and we need to divide by 100. So 11,200 divided by 100, and then we're going to square root that. So that's going to be the square root of 112, which based on my answers has got to work out to be 10.6 micrometers. There we go. Okay. So the key takeaway here is that the average displacement of the particles was 0, but the root mean squared displacement of the particles is not 0. Distance of 3 millimeters in a time t. At what time would the blood have diffused 9 millimeters? So once again, try this yourself, but here's the answer. So we know that the RMS distance is proportional to the square root of time. So doing the opposite of that, the amount of time it would take would be the RMS distance squared. So it goes from a distance of 3 millimeters to a distance of 9 millimeters. So it goes 3 times farther away. Therefore, it's going to take 9 times longer to get there. So T2 over T1 is equal to RMS2 over RMS1 squared, which is 9 over 3 squared, which is 9. So 9 times longer. Okay, so then that brings us to Fick's law of diffusion. So Fick's law of diffusion talks about the flux. Flux is the number of particles that are diffusing across some area in a given number of seconds. Okay, it is going to be directly proportional to the steepness of the concentration gradient. So if you have high concentration here and low concentration here, diffusion will happen from the area of high concentration to the area of low concentration, and the rate of diffusion is determined by Fick's law. Read that. I don't have anything else to add for this slide. If we look at a special case where we have a box with a barrier dividing two parts of the box, and in the initial conditions the concentration of one area is 0 and the concentration in the other area is C, over time we will have a diffusion of particles from the area of high concentration to the area of low concentration, and the rate of diffusion will depend on the thickness and the permeability of the membrane. But if we wait a long enough period of time, the concentration in both regions will reach an equilibrium, and at that point the number of particles diffusing across the permeable membrane is equal in both directions, so the concentration doesn't get out of whack again. It always stays consistent from one side to the other. Here's a question you can try. If you have two regions of space separated by a long tube, and region 1 has a fixed concentration of C1, whereas region 2 has a concentration of 0, what does the concentration gradient look like inside the tube? So basically, what's the concentration at each point along the tube? So if we were to graph the concentration as a function of the distance along the tube, in order to get the right answer here, we'd have to recognize that at the left side of the tube, the concentration would have to be C1, and at the right side of the tube, the concentration would have to be 0. If we look at our options, that would eliminate both C and D, and so then we would choose from either A or B. Both are reasonable answers. In this case, because it's a one-dimensional example, B is the correct answer. It's a linear gradient. Molecules are placed in one corner of a sealed box full of air. Which of the distributions below best represents the red gas molecule distribution in the box after a very long time, i.e. what's the equilibrium distribution? So some people might want to answer B or possibly C. Not many are answering D because the concentration here is low. However, the key term here in this question is that it's after a very long time, so we're talking about an equilibrium distribution. Therefore, the answer is A, because that is where the distribution is uniform and there will be no more diffusion happening. So things to take away, go ahead and read those. I don't have anything to add. I would just read them for you. So pause the video and read the takeaways. And then we get to the barometric formula. So this is just to remind ourselves of the fact that some fluids are compressible and some are incompressible. If we're talking about water, how does the pressure change with depth? So give that a try yourself. The correct answer is that we have to use hydrostatic pressure. So in other words, pressure is equal to rho g h. So that's a linear relationship. So as the depth increases, so too does the pressure. Then we look at the same kind of question if we're talking about air. How does pressure change with height in air? So then because air is compressible, you're looking at using the barometric formula. And you can take a look at that on your formula sheet, but it's basically a decaying exponential. And so, B makes no sense. Can't be C because that's linear. Some people might vote for A, but it doesn't actually have the correct shape for a decaying exponential. So D is the correct answer. As you get further up from the ground, the air pressure drops. The gas's compressibility, combination of both hydrostatic pressure and gravitational pull on the molecules. Because Earth is pulling down on the air, it's trying to pull all the air towards the surface of the Earth, but then that's being resisted by the pressure created by compressing gases. And so it's sort of this balance between these two forces acting on the air to create a concentration of air particles at various altitudes. So what we get then is that particles will sediment under gravity. So based on their thermal energy, there will be some distribution of particles. We'll get more particles near the bottom and fewer particles near the top of any container. And here we can include the atmosphere as a container. This leads us to Perrin's experiment. So Perrin's experiment was basically to look at these small little balls that had slightly greater density than the fluids they were being placed in. And it doesn't sound like a very exciting experiment, but he would literally count the number of these particles that he found at each, at each depth in the fluid. And what he found was that they followed this sort of decaying exponential relationship. So you could actually represent mathematically the number of particles in a given region compared to the number of particles that were on the bottom of the container. About the number of particles compared to the number of particles that are at the very bottom, which is given by this equation here. So that's the relative number of particles at any height relative to the number of particles that are at the bottom. And it depends on the density of the particles, the density of the fluid, the temperature, and that sort of stuff. So then we can do a more mathematical question. This one takes some time to work out. You reach for a shelf to grab a well-settled vaccine made of a weakened virus particle suspended in serum. The virus has a diameter of 100 nanometers with a volume of 5 times 10 to the minus 22 cubic meters. So in the equation we have volume, so that's the thing that we're going to use, 5 times 10 to the minus 22. the virus is twice the density of water. So the density of the virus would be 2 times 10 to the 3 kilograms per meter cubed. Therefore, if I do density minus the density of the fluid, density of water is 1 times 10 to the 3. So if I subtract those two, I'm going to get just 10 to the 3 kilograms per meter cubed. If you don't shake the vial, what's the relative? So if we don't shake it, that just means that we're talking about the equilibrium distribution. So Perrin's experiment, what's the relative concentration of virus particles you suck up 2 millimeters from the bottom? So the change in height is 2 times 10 to the minus 3 meters. And then they don't tell us the temperature, but we can assume room temperature or approximately 300 Kelvin for this sort of a calculation. So then all we have to do is start plugging in values. So the number of particles is going to be, so volume 5 times 10 to the minus 22 times g, which is about 10, times the height, which is 2 times 10 to the minus 3, times rho minus rho of the fluid, so 10 to the 3, all divided by Boltzmann's constant, so that's 1.4 times 10 to the minus 23 times the temperature, so that's 300, which is 3 times 10 to the 2, so 3 times 10 to the 2. There's a fair number of things that we can cancel out here without having to do too much work. Obviously 10 to the minus 22 cancels with most of those, so that's just minus 1. 10 to the minus 3 cancels with 10 to the 3. And then I have 10 canceling with that, and then that cancels with that. So you can work this out on your own with the aid of a calculator if you so choose, but I think what I get is 5 times 2 on the top, which is 10, and 1.4 times 3 on the bottom, which is like 4.5-ish or so. So that's about e to the negative 2, which is like 1 over e squared, which is pretty close to 1 over 10, so about 10%. There we go. So you would suck up about 10% in concentration. So Perrin's experiment and the Boltzmann equation only describe what you find eventually. Doesn't tell us anything about how fast things sediment. That's determined by the terminal velocity of a particle. So this was derived in the course notes in chapter 4. You can take a look at that section. But this is the equation that we get for the terminal velocity of particles. The equation, we already have all of these pieces of information except for we're given the diameter, so we need to convert that to a radius. It's 50 nanometers, which is 5 times 10 to the minus 8 meters. So putting all this into the equation, 2 times 5 times 10 to the minus 8 meters squared times 10, density minus the density of the fluid is 10 to the 3, divided by 9 times the viscosity, 10 to the minus 3. So working that out, 5 squared is 25, so this is going to give me 2 times 25 times 10 to the minus 16. 10 times 10 to the 3 is 10 to the 4. And I'll move the 10 to the minus 3 up to the top, 10 to the 3 there. All divided by 9. Looks like I'm out of space again. Anyway, we can work this out, and let's see. So 2 times 25 is 50. 50 divided by 9 is about 5. And then we've got 10 to the minus 16, 10 to the minus 12, 10 to the minus 9. So 10 to the minus 9 meters per second. So that's going to be 5 nanometers per second, which is quite slow. So how often will you need to reshake the vial? Not very often. I think it works out to a number of days.